vision algorithms based on convolutional neural networks have been demonstrated to be vulnerable to adversarial attacks, where small alterations on an image can cause a model to become unstable. This characteristic is known as lacking robustness. In fact, there are many examples in the literature where all we need to do to fool a computer vision algorithm is to alter one pixel. This is referred to as one pixel attack. Now, with these one pixel attacks are very challenging to defend against because many of the explainability techniques we have highlight a region of an image which makes it very difficult for a human examiner to visually detect the presence of a one pixel attack. The work we will review today highlights proposed solution to this difficult problem. Hello, everyone, and thanks for joining us. My name is El-Sharif, and I'm a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Haohan Wang. Haohan is a PhD candidate at Carnegie Mellon University, working with Professor Eric Ching. His research interest centers around trustworthy machine learning, supported by statistical analysis and covering a spectrum of applications, including computer vision, NLP, and computational biology. Haohan is an award recipient of the next generation of biomedicine by the Broad Institute of MIT and Harvard. His survey paper on the origin of deep learning is considered one of the most influential data science papers in 2018 by media from Open Data Science Conference, and we're very lucky to have him. Haohan will present his paper, High-Frequency Components Help Explain Generalization of Convolutional Neural Networks. It is a very highly interesting presentation, and I'm looking forward to it. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn the presentation over to Haohan. Please take it away.
Okay, thank you. Thank you for the very wonderful introduction. And hi, everyone. I'm Haohan Wang from Carnegie Mellon. And today I'm going to share one of my works entitled High-Frequency Components Helps Explain the Generalization of Convolutional Neural Networks. It was accepted by CVPR this year as an oral paper. Okay. So for this presentation, at first, I will introduce some of our empirical observations with the highlight on the misalignment between models and human. And then with our observations, we attempt to offer several explanations of the previous generalization behaviors that we observed. Okay. So first, for those empirical observations. So let's say we have a model. In the paper, we use ResNet32 as an example, and we have a sample. If we feed the sample into the model, we can get the prediction as this. In this case, the model is quite confident that this image is a mobile. And then we put this sample with, we transfer this sample with Fourier transform into its frequency domain, and we choose a radius. And then with that radius, we cut the frequency domain into low frequency and high frequency counterparts. Then with each counterpart, we reconstructed the image. And and from here, we can say that the image reconstructed from the low frequency component looks almost identical to the original image to a human, while the image reconstructed from the high frequency component is basically noises to human. And however, when we fit these two images back to the same model, we can say here are the prediction confidences, where for the low frequency image that looks identical to human, the model considered it to be something else. However, for the high frequency image, the model still predicts it to be a mobile. And just in case someone is interested, this is a rescaled version of the high frequency image. As here, those signals are after the reconstruction, those pixels are pretty small. So basically, they are not visible to human. So after even after we rescaled it, it still looks like a random noise instead of some mobile structure thing. Okay. And although this is not a random image of the dataset, this is not the only one. So in our paper, out of the 10,000 testing samples of CIFAR-10 dataset, we identified around 600, 700 images to have this problem. Well, this number is not maybe not that big, but we consider that this observation is significant enough to raise an alarm. Okay, here are only 8 other examples of the same phenomenon. Okay, and then we try to ask the question like, why such thing can exist? And we believe that there is a challenge of robust machine learning nowadays. When we perform machine learning, we collect the label and the data, and then use those label and the data to train the model. However, in the data, there could be some semantic signals. For example, what makes a car. And there could be some high-frequency components also in the data. And those semantics is how we define the label. However, within the data set, there could be some correlations between the semantic signal and the high-frequency components. Because of the correlation, there could exist some associations between the label and the high-frequency components. And then while a model is trained, a model is only asked to update its parameters to reduce the empirical loss. The model cannot really differentiate semantic signal from other signals. So a model, while trying to maximizing the accuracy it may learn to pick up both signals and in the phenomena that we have just talked. Okay. And with that observation, we try to use this to try to explain some generalization behaviors of the model. From the first one will be the recently very heated discussed the trade-off between accuracy and robustness. Okay, so there are quite a few previous theoretical understandings of accuracy versus robustness, and most of the literature fall in 2 categories. Well, one trend believes that there is a trade-off between the accuracy and the robustness, while the other thing considers that a model can be both accurate and robust. And while these papers offer rigorous proof and very sound arguments to support each own points. Here we notice that there is a unified pattern behind these papers. Basically, we believe that within a collection of data, the samples have some non-robust features and as well as some robust features. And the arguments below the left set tend to argue that a model must predict through some non-robust features in addition to robust features. Therefore, the non-robust features can lead to high accuracy, while they cannot be used when we care about robustness. On the other hand, the right-side arguments tend to argue that a model can predict only through robust features if we regularize those models properly. Therefore, we can argue that in the future, we may eventually see both accurate and robust models. So these are the previous theoretical arguments, and let's say here, those arguments actually align very well with our empirical observations. In fact, many of the papers appeared on the previous slide are released after our paper. So here, we argue that with this figure, we argue that within the data set, there exist semantic features and high-frequency components, and accuracy-driven models are encouraged to use any features, either the semantic or those high-frequency components, while robustness-driven models are encouraged to use semantic features. In our paper, we also attempt to offer some formal proofs regarding this, and if you are interested, please have a look. Okay, so this is the first part. And then we try to use our technique to explain some interesting techniques with the highlight on the efficiency of batch normalization. And other than batch normalization, we try to leverage our techniques to understanding several techniques. For example, how the batch size will affect the training performance, and how other methods such as dropout, batch norm mix-up, adversarial training will affect the model's tendency in learning semantic or high frequency. And we also explored the same experiment regarding different network architectures and optimizers. However, within this presentation, I will only talk about batch size and these training techniques, which I think are the most interesting part. Okay. So before that, this is the remainder of the experiment setup. This figure is from a couple slides ago, and where we map the image to its frequency domain, and we choose a radius to cut the frequency domain into low frequency and high frequency parts. And that will reconstruct those images. The following experiment will heavily rely on the choice of this radius. And for example, most of those experiments will set up as the following. We choose the radius to be 4, 8, 12, and 16. And then we reconstruct by the low frequency part and the high frequency part. So these ones annotated with low are the what we consider low frequency signals or semantic signals. And these ones are the high frequency signals. And another convenience is that we can say that those solid lines always represent low frequency or semantic signals, while these dashed lines are representing the high frequency signals. Okay. With this, we try to train the same model with different batch sizes. And this figure has a lot of lines, so let's try to look them more carefully. So maybe let's look at this middle one. We trained the model with 100 epochs, and the y-axis is the accuracy for these different choices. And this gray line is the training accuracy, while the black line is the test accuracy on the original test dataset. Well, these lines are the test accuracy when the test dataset are perturbed or changed according to our choices. And once again, those solid lines represent the low frequency or semantic signals, while the dashed lines represent high frequency signals. And here we can see a quite interesting phenomenon. When the batch size are small, the model tend to learn more high frequency signals in comparison to the one on its right hand side. And however, the model tend to get a better accuracy. So with this, our argument is that when we use smaller batch sizes, the model seems to tend to get higher accuracy, while the model also seems to exploit more high-frequency signals. Well, on the other hand, when we increase the batch sizes, although the accuracy seems to be smaller, the model seems to have a smaller generalization gap, which means the differences between training accuracy and test accuracies. And we believe that's a result of the fact that the model tends to exploit less high-frequency components. Okay. And then we also use the same technique, the same set up to compare different training techniques that we use. We ran the experiment with the vanilla setting, with the setting that we use dropout, and mix up batch norm and adversarial training. Mix up is recently quite a popular method that used to help the model to improve the prediction accuracies. And the idea is basically during training, we select, in addition to the original training data set, we randomly sample, like, for example, two training data set and linearly interpolate them. And the label is also linearly interpolated. So it seems like we create additional data by just mixing those two samples as both the features and the labels. And although that technique is fairly simple, it plays a quite significant role in helping the model to improve the prediction accuracy. And batch norm stands for batch normalization, and which I believe is a very well-known technique. It's essentially about rescaling the input of each layer. And also it is very well known for improving the test accuracies, especially for vision models. And adversarial training is the method popularized by adversarial attack defense community. It essentially is about during training that we augment the training samples with samples that are adversely attacked during training, and those attacked samples, training samples, help the training process to develop the model that is more robust to adversarial attacks. Okay. And here we notice that several very interesting phenomena. First, maybe less interesting, that dropout is roughly similar to the vanilla model. However, it looks like mix-up is quite interesting in the sense that mix-up encourage the capture of high-frequency signals. As we can see here, the dashed line get raised up during the later phase of the training process. And this could also very intuitively explained as during training that the mix-up is essentially like mixing those samples without the understanding of whether those samples are for whether those features are for, say, the semantic, the shape, or texture. So mixing them while mixing the label could encourage the capture of any features that is associated with the label, such it could encourage the capture of the high-frequency signals. And next, we can say that adversarial training barely captures any high-frequency signals. This is also very intuitive, as adversarial training, especially here we use PGD as the threat model during training, is essentially helps remove the texture of those images. And as a result, the adversarial trained models barely capture any high-frequency signals, and this may also explain the reason that those models tend to be more robust to similar adversarial attacks, as we will see later. And the most interesting part is this one about batch normalization. As we can see here, batch norm captures a significant amount of high-frequency components. And this could also explained quite intuitively. As we see previously, when we reconstruct the images, the image reconstructed from the high-frequency components are barely visible to human, although they are predictable. And one reason is that those signals are of very small magnitudes. And batch norm, by using the rescaling technique, it probably rescales those predictive features to a much larger magnitude, and those features can be much easier used by the model. And as a result, we noticed that batch norm, while improving the test accuracy a lot, it encouraged the capture of a significant amount of high-frequency signals. And also this aligns very well with previous observations that batch norm encourages adversarial vulnerability. And for example, here's a paper to support this argument that batch norm could be one of the reasons of the adversarial vulnerability. Okay, so this is the second part. And the third part, we try to talk about another interesting phenomenon, which is generally known as a paradox in learning, or maybe another way to know this phenomenon is like this, people call it like the thing talked about the rethinking generalization paper. So just to recap the observation they have, well, they first train a model in a standard case. Basically, we feed the data into the model as it is, and we notice that neural networks can predict pretty well. So the neural networks do not easily overfit, and it does not just memorize those samples. However, if we shuffle those labels and we feed the label shuffled data into the model, we notice that neural networks can still reduce the training error even if the labels are shuffled, and which means that it has enough capacity to memorize every sample. And by comparing these two cases, there is a question that raised. So if the model has enough capacity to memorize the data, why it does not choose to memorize data in the first place? Okay. So here we try to offer some hypotheses to explain that paradox. First, during the standard case, we argue that the model will first pick up the low frequency components and then gradually pick up high frequency for higher accuracy. But during the label shuffled case, the high-frequency components and low-frequency components are treated equally because the strong association between low-frequency components and the label is erased by shuffling. Okay, and to validate those hypotheses, we did the following experiments. And here we trained the model with the original samples, but we also reported the training accuracy on different copies of training data. So again, we use this the same technique. We choose a radius and split the data into different components. And here are the copies of training data with low frequency reconstructed samples with different radius. And first of all, we noticed that for the natural label case, the model only needs 100 epoch to get a reasonably high accuracy, while for the label shuffled case, this needs up to 300 epochs. And also we noticed that, for example, for this green curve, the model tend to, in the natural case, the model tend to learn a reasonably good amount of low frequency components at the very beginning. However, in the label shuffled case, it seems that the model never cares to learn these low frequency signals. And for this roughly blue curve is basically the same story. Okay, and so we notice that the model tends to pick up low frequency components. And then we ask, why does the model tend to pick up low frequency components? And there are previous explanations says that SGD tend to pick up simpler functions. There are all kinds of analysis on this. And for example, through Fourier analysis or through the recently very popular neural attention kernels. And here we offer another direction. We argue that there might be some data-oriented explanations, that the low-frequency components are simply more generalizable because the data is created as by human according to the low-frequency components. And to validate that, we train the model on low-frequency components or high-frequency components and then test on the original samples. And here we can say that, well, on different settings, well, the model can get reasonably high training accuracy, whether it's trained on low frequency or high frequency, the test accuracies are quite different. which seems to support our argument that the low-frequency components are simply more generalizable. And finally, we try to use this to explain that this is one of the explanations to adversarial vulnerability. And just to catch up the background, adversarial examples is essentially this story that with a model with a sample that model has a good prediction, and if we add some noise that is barely visible to human, the model will predict to be something else. And I believe that most of us who have seen adversarial examples has already seen this figure. I think this figure is like too popular that I probably have to add it to my presentation. And adversarial training is one of the most efficient way to define some model against this kind of adversarial attacks. Okay, and regarding this direction, we study the connections between smoothness and adversarial vulnerability, where first, through some proofs, we can show that smooth convolutional kernels will probably pick up less high-frequency signals. And then this may lead to the question like whether a smooth convolution kernel can be more adversarially robust. And here by smoothness, we mean that it's smooth in the context of signal processing. That which means for a convolutional kernel that the changes between adjacent weights are small. Okay, and to do that, we visualize the convolutional kernels of a model that is trained in the vanilla sense and with the adversarial training techniques. And we notice that more adversarially robust models tend to have smoother kernels. And then we also try to regularize the model to have even more smoother kernels, and then we test the adversarial vulnerability of these models. However, the adversarial attack can still quite successfully attack this method. So unfortunately, the reverse of the above argument is not always true, which means that we believe that the high-frequency components is one of the reasons of adversarial vulnerability, but probably not all of the reasons. Okay, then in our paper, we also have some other discussions about the results that beyond image classification. For example, in object detection, when we replace the standard test image with the low frequency components, we notice that some images can lead to higher performance while some lead to lower performance. This, in my opinion, means that the story is more interesting than what we have seen in the image classification that may require a deeper look into it. Also, there are also similar problems that we observed through other papers in the, for example, in natural language processing, where we use the natural language inferences as an example, where essentially the problem is that the same like where there are some false associations between the semantics and the distribution of words. And considering the timing of the presentation, probably I will not discuss the details of this. And finally, I have to just try to pitch an idea towards the robust machine learning, where as we have seen in this figure in the previous slide, that we argue that an essential essential reason for the machine learning models to be not robust enough is that the model could pick up some superficial signals, which is high frequency signals in this presentation. And this could lead to very unintuitive behaviors of the model, and that seems very non-robust when we define robustness according to a human. And so we argue that towards robust machine learning, one of the central solution is probably to cut this tendency of how the model learns the tendency of the model that learns the superficial signals. Okay, and this is all I have today. Thank you very much. And here are some of the contacts and the main reference, and the code is also available off here. And in case someone is interested, this is one of my brief discussions of robust and trustworthy machine learning in my advisor's course. And finally, thanks to the AISC for holding this event, and it's a very glad experience, and thank you very much.
Thank you, Haohan. I appreciate the presentation. We have a number of questions that we would like to discuss with you. First, a couple of questions from Alexei, complimenting your paper, and maybe he'll start with any theory on why BATCNOM would cause it, or how many, maybe I'll start with how many labels in a task, what are the random choices baseline for accuracy?
You mean in my experiment? How
Yes.
many? So for most of the experiments, we use the standard CFR10 dataset. So there are 10 labels, and the random accuracy is probably around 10%.
Okay, and he's asking about a question about batchcom. Why would batchcom cause any issues with accuracy here?
You mean the
Yeah, if you can clarify your question, honestly, we're not really sure. How many labels in a task? What would the random choice be for accuracy? And then any theory as to why batchcom would cause it?
I see. So maybe let's revisit this figure first. So as we see here, that the high frequency signals, like the image reconstructed from high frequency signals, are also predictive, but they have very small magnitudes, so it's barely visible to human. And batch norm is essentially rescaling all those features during training, and we believe that one of the reasons is that batch norm rescales those predictive features that previously have very small magnitudes to some reasonable magnitude, so that those features can be more easily used by the model.
Okay, excellent. Now, Haohan, we've received a number of inquiries from industry, from people in the community interested in your work and interested in maybe reproducing your results and trying your approach on their data sets, if you will. Help us understand what is it in your GitHub repo that people have access to and they're able to try to reproduce what you've explained to us here.
Sure.
And verbal, you don't have to get into the actual code, but super high level, what can people reproduce from?
Okay, maybe it's more convenient for me to get to the code.
Okay, that's fine if you prefer to do that.
Okay, so this is the code base, and here we have a explanation of the code, and here are the major arguments of this paper, and there are also other discussions in the paper, which I have covered most of them.
Mm-hmm.
And also we have the code structures, which this is basically the main code to replicate our results. And here, here we have the explanation. So our code is actually pretty simple to replicate. So we only need probably these informations.
Okay.
So most of these are used to, so this one is probably a very major component that used to generate the low and high frequency data that we rely on a lot. And these two attack helper and PGD attack are only used during the in the section that we talk about adversarial attacks.
Okay.
Yeah, and we have the dependency information here.
Mhm.
Yeah, and oh, by the way, the code, the experiments are run in TensorFlow, but one of my co-authors also generate a PyTorch version of it.
Okay. Yeah, this definitely is helpful, specifically for those who want to reproduce your results and follow along and maybe potentially extend the work in different domains. So that was very helpful. Thank you.
Thank you.
So maybe we'll start with a question that you actually included in your paper. Are high-frequency components just noise? I mean, in your paper, you made a statement. Our observations suggest that signal CNN exploits is more than just random noise. Can you please expand on that concept? Why is it that HFC is not just noise?
Yeah, that's a great question. So we also have that concerns that the HFC might be just noises and during our experiments, and to validate that we try some other experiments. For example, instead of reconstruct the image through low frequency or high frequency components, we first perform SVD on the data and then reconstruct the data on the salient eigenvalues and those trailing eigenvalues, where those trailing eigenvalues are usually believed to be noise, and things this like the singular value truncation is one of the most popular denoising methods in the region, I guess. So we repeat the same experiments with the image reconstructed according to eigenvalues, and we do not observe the same phenomenon. And with this, we argue that it's probably more than just noise. If it's noise, then probably with training eigenvalues, we probably should observe the same behaviors of those models.
So would it be a bias, not noise? Is that a fair way to characterize it?
Yeah, I think so. I think it's more like a bias inside the data. Like now people call it a data set bias.
Okay. Now we've got a question from Slope Dawn. How does it compare with CNN that are biased toward texture?
I see. That's also a great question. We believe that high frequency components is one of the reasons that CNN is biased towards texture. And so basically, high frequency components is one kind of texture, right? It also depends on how you define texture. I feel like texture is more like well, it helps to convey the idea. It's more like a subjective opinion of the components. And here, a major contribution is that we define the texture of the problem in a rigorous way. But on the other hand, that people argue that CNN is biased toward texture could mean some other texture, and so I will say that high frequency is one of the textures.
Okay, excellent. Thank you for that clarification. Now, your work identifies sensitivity of CNN to high frequency components. Do you believe that sensitivity exists for any deep learning methods on a computer vision task, or is there something specific to CNN?
Yeah, I do believe so. I believe that this is more like a data problem.
Yep.
This is like something encoded in the data set, and most of the techniques that in our days wants to get a reasonably high predictive accuracy will need to explore some other superficial features.
Okay.
So yeah. So if other models that can get equivalently high accuracy without careful calibration of these problems, will probably suffer from the same thing.
Now, help me envision, how do you potentially see people using this insight about high frequency domains? Do you envision maybe diagnostic tools that are used by algorithm developers to find which of these algorithms are robust to or not? Do you envision this in maybe filtering training data, so we're not training to noise to begin with? What's the best, or what do you envision as the approach to utilize the insight that you've shared with us today?
Well, thank you. Thank you. That's also a very, very great question. And so first of all, I think the immediate usage of the idea is to offer some convenient test of the models. So as we have seen here that although the models can have high predictive accuracy, it's probably not see the data as we do. So by some very simple tests like mapping the data into low frequency domain and test the accuracy again, we can have some rough idea about how robust the model is. I think that's the most straightforward usage. And on the other hand, can we directly use the technique to train models that are robust to high frequency components or superficial features? That's probably need some very careful design and more well-developed techniques at this moment. For example, some people have raised this question previously, like what if we train the models with low frequency data only, and then the image with full frequency spectrum will be considered as out of domain images, and again, the performance may not look very good on those images. So so I think the like filtering them during training may not be a solution, but filtering those high frequency during testing, if we are allowed to, it could be a nice solution. And another solution could be like trying to augment the training data with different high frequency components. It's essentially like the adversarial training. So basically, during training, we have seen the model with the same semantic or shape, but with different high frequency or texture, and then the model will force to learn the semantic information.
Okay. Now, there's a question about the part that you said you did not have time to do, but they really want you to talk about it, the how would it translate to NLP models like transformers. So if you could maybe briefly present a little bit on that, that would be great.
Sure. Yeah, let's just use this. So basically, we talk about the task called natural language inference, and it's a task about for a model to classify a pair of two sentences, whether the sentence is entailment, which means that the first sentence implies the second, or like a contradiction, which means the first, if the first sentence is true, it means the second sentence is not true. And neutral, which is the third label, which means that the two sentences are basically independent. And the data set is generated in a way that they invite Amazon Mechanical Turks to write the second sentence given the first sentence. So when those workers try to finish their tasks as soon as possible, they invent some very convenient way. For example, if the first sentence is like a rabbit is running, then they will add a not to it. Basically, the rabbit is not running to create a contradiction label. And then with that, there are some connections between the label and the worker's word choice of the second sentences, and also the worker's word choice leads to the distribution of the words. However, there shouldn't exist any association between the semantic and the distribution of words, because the basically those shouldn't encode semantics. However, there are in the data set because of this part. And we designed some experiments to show that. Basically, we argue that if those two sentences are contradiction, then when we swap those two sentences, the accuracy should be the same. And if those two sentences are neutral, then when we swap those two sentences, the accuracy should be same again. However, when we do the experiment after swapping those two sentences, we see some reasonably big performance drop after we swap, which means that the dataset seems to have the same issues. And so this is one of the work. And I think in the NLP field that people are very well aware of the problem that those models are trying to leveraging some keyword information of those sentences instead of reading the entire sentence.
Okay, thank you. That was, and I'm receiving notes here from the audience. Thank you for that explanation. Appreciate it. Now, maybe I guess the question is, we always have the option to do just adversarial training, right? Pick a data set that we know has certain types of attacks played in and just train our models through adversarial training. Why is it better to find dependencies on high frequency domain through just a frequency spectrum, if you will, versus adversarial training?
I see. So adversarial training is more like a solution to this kind of problems, right?
Yep.
Yeah. I think the main one of the main contribution that we make is that try to argue that the central problem of, for example, adversarial vulnerability may not be something on the model, but it's more on the data, which I think is also accepted like understanding nowadays. So through all the techniques, like we argue that the problem is, or maybe not the problem, but the challenge that we need to solve is the data. That the data have this kind of underlying relationships that we need to account for it. And I believe this could open several new directions and there are new techniques for the machine learning. And for adversarial training, as we argued that adversarial training can be very convenient, that after we understand this, we try to say, like, if we can directly make the model prone to high frequency signals, that could be more adversarially robust. Although here we cannot offer a general guarantee, we do notice that it could improve the adversarial robustness for some attacks. And that could also be an interesting add to adversarial training, as smoothing those kernels is like basically requires no computational efforts if you compare it to training a model in the first place, let alone compared to adversarial training a model.
Okay. Now, if we can stick with the problem is the data for a bit here, do we have benchmark data sets out there that specifically address this bias, if you will, towards high frequency components? I know you've used the CFAR10 data set in your experiments, but it's a general data set for computer vision. But do you feel there's a need out there to establish a data set that specifically addresses this need?
Yeah, that's also a great question. I think, like as agreed by many people in the robustness field, the benchmark data set is in a very urgent need nowadays, and to answer that question, we might need to say, like, split the what we need in different sub areas. For example, if we are talking about adversarial robust, probably we don't really need another data set, as we have all kinds of adversarial attacks that could generate those data sets given a model. And on the other hand, the robustness is not only about adversarial robust. People also working on cross-domain robustness, where they train a model on one dataset and test on another related dataset. For example, domain adaptation as one example. And there we also have some interesting dataset, but I think we need more. We need probably a lot more in terms of different tasks, in terms of different data sizes, and maybe different modalities. Yeah.
Okay. It's excellent. So I think that's a very excellent point to end on. Do you have any final thoughts before we wrap up the session? Yeah.
Yeah, I think these questions are pretty good, especially the one that about what this paper can be used for. I think that could be used as a very good final thought. When I work on this paper, I kind of very briefly wrote a concluding section that I try to argue that the development of machine learning need to vary about the robustness and maybe testing with the low frequency counterparts is one of the most convenient way to test the robustness.
Okay. Haohan, I thank you for a great presentation, and I thank all of those who joined us online. This session is better because of your questions and participation. Thank you, everybody. To see more free content like this, please visit our website at AI.SCIENCE and log in to access our slides from this and other session. Also, make sure to subscribe our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.